Okay, in this class we will discuss a problem on stresses on octahedral plane. So octahedral plane means it is a plane on which the direction cosines are equal. That means direction cosines of the plane are defined as n and n. All are equal means it will be 1 by root 3. So it is very important. If they ask you to find the stresses on octahedral plane, we have to take the values of direction cosines, all the values as 1 by root 3. This you are going to get by using this relation m square plus n square is equal to 1. In the case of octahedral plane, all these three values will be equal. So if you substitute all the three equal, even if you solve, you are going to get L is equal to M is equal to N is equal to 1 by root 3. So that is understood. So they won't give the values of L and N. You have to take yourself it as 1 by root 3. Now here also, he has given the stress tensor at a point on the octahedral plane. So here, this is stress tensor. So by comparing this stress tensor with this notation, so we can write down the values. Sigma x is 200 MPa, sigma y is minus 100 MPa, sigma z is minus 100 MPa. Just we have to compare these two. Tau xy is 200 MPa, tau yz is also 200 MPa, tau zx is also 200 MPa. So all these three values, shear stress values are equal, and normal stresses are like this. So here the positive value gives tension stress, negative value shows compressive stress. So we are not worried about the nature. Anyway, so at a point on the octahedral plane, so the stress tensor is defined like this in a three-dimensional stress system. Now he has asked to find the stresses on this octahedral plane. So here, by using Cauchy's formulae, in the last class also I had explained about this. So first we have to find out three components of stresses. Components of stresses on the plane. So those are given by Tx, Ty, Tz. So you know that this Tx is the component acting in x direction, Ty is the component acting in y direction, and Tz is the component acting in z direction. So once you get these three stress components, the resultant stress can be found out using this formula. Root of Tx square plus Ty square plus Tz square. Now to find these three stress components, we are going to use these three equations. These three equations are called as Cauchy's stress formula. So it is very easy to write this. So the stress component along x direction Tx is given by, so you can see the first row of the stress tensor. So just take each element of the first row and include that direction cosine with each element and add. You are going to get Tx. For example, sigma x into L, the first element corresponds to L, second element corresponds to M, third element or third column corresponds to L. Now if you write in that way, sigma x into L plus tau xy into M plus tau xz into N. So this is the stress component Tx. Now if you substitute the values, so sigma x value is 200, L is 1 by root 3, tau xy is 200, M is 1 by root 3, tau xz is also 200, N is 1 by root 3. So please note that N, M, N, they are all equal on an octahedral plane. So octahedral plane means it is the plane on which direction cosines are equal. That means that plane is making equal angle with the x, y, z axis. That is the meaning. So cos of the angles alpha, beta, gamma. Here alpha is equal to beta is equal to gamma. So cos of that angle is nothing but the direction cosine, as we already studied. So similarly, this if you simplify this, you will get 346.4 MPa. That is the Tx value. Ty is given by, you take the second row. So tau xy is 200 into L, which is 1 by root 3, plus sigma y into M, so which is minus 100 into 1 by root 3, plus tau yz is once again 200 into N is 1 by root 3. Here if you simplify this, you are going to get 173.2 MPa as the value of Ty. Similarly, by taking the third row, you can get the value of Tz. Tz is tau xz into L plus tau yz into M plus sigma z into N. Once again, by substituting the respective values and simplifying, you are going to get this also as 173.2 MPa. So like this, by using Cauchy's stress formula, we can find out the stress components along x, y and z directions respectively. After getting these three stress components, we can find out the resultant stress by using this. T is the resultant stress. By using this formula, root of tx square plus ty square plus tz square, just substitute these values, square it, add them, take the square root. If you simplify, you get 424.26 MPa as the resultant stress. So this is one state. By using Cauchy's formula and the resultant stress formula, we can get the value of T. Next, we have to find out the normal stress. So normal stress is also given by this equation. So Tx into L plus Ty into M plus Tz into L. That is the formula to find sigma. Sigma is the normal stress. It can be either tensile or compressive. So substitute the values. So Tx is 346.4 into L is 1 by root 3 plus Ty is 173.2 into 1 by root 3 plus Tz is 173.2 into 1 by root 3, and if you simplify, you will get 400 MPa. Since the value is positive, we can say that it is tensile. Tensile in nature. Normal stress can be either tensile or compressive. If it is positive, it is tensile. If it is negative, it is compressive. Now, once you get these two, shear stress, normal stress and the resultant stress, you can find out the shear stress on the plane, that is tau, which is nothing but root of t square minus sigma square. So t value you have got here, sigma value you have got here. If you substitute and simplify, you will get 141.4 MPa. Now, how to show that on the plane? Now, if you take this as the octahedral plane, which makes equal angle with all the three x, y, z directions in 3 dimensions. So, normal stress here it is tensile. Tensile means it will act away from the plane. So, it is like this. So, sigma acts like this. So, I have shown here 400 MPa, and shear stress acts like this. Parallel to the plane is shear stress. Perpendicular to the plane is normal stress. So 141.4 it acts like this. Now the resultant is like this. So sigma is acting like this, tau is acting like this. The resultant stress T will act like this. So the T is the resultant of sigma and tau. So this is how you can find out the stresses, that is normal stress, shear stress and resultant stress on any arbitrary plane. So in this case, particularly he has asked for octahedral plane. The characteristic of octahedral plane is the values of L, M, N, they are equal, and they are equal to 1 by root 3, and the remaining procedure remains the same. So in this class, we will derive the stress strain relationship for a 3-dimensional stress system. So we know in strength of materials that stress is directly proportional to strain within elastic limits, and if you take the ratio of that stress to strain, that is called as the Young's modulus E, sigma by epsilon. So I am going to use sigma for the normal stress and epsilon I am going to use for the strain component. Now to understand for a 3-dimensional stress system, let us consider a 3-dimensional element like this, which is subjected to normal stresses in all the 3 directions, x, y, z directions. So I have taken here all the stresses are tensile stresses, they are acting away from the element. So sigma x is the normal stress in x direction, sigma y is the normal stress in y direction, sigma z is the normal stress in z direction. So when a element is subjected to stresses like this, definitely there will be a change in volume. So change in volume, if it is subjected to tensile stresses throughout, then there will be increase in volume. If it is subjected to compressive stress, then there is decrease in volume. Suppose if it is combination, depending on the magnitude of the tensile and compressive stresses, the volume may increase or it may decrease. Anyway, there will be some change in volume. Now here, I will take E as the Young's modulus of the material of the element. Mu is the Poisson's ratio of the material of the element. So you know that Young's modulus is defined as the ratio of linear stress to linear strain or normal stress to normal strain, and Poisson's ratio is defined as the ratio of lateral strain to linear strain. So those things we have done in strength of materials. Now, to derive this stress strain relationships, that is sigma epsilon relationship, so we will consider generalized Hooke's law first. So generalized Hooke's law is a combination of Hooke's law and principle of superposition. So generalized Hooke's law can be written for a three-dimensional system like this. Suppose if you take epsilon x, epsilon y, epsilon z as the strain along x, y, z directions respectively. So they are the resultant strains actually. This epsilon x, epsilon y, epsilon z will be due to all the three, sigma x, sigma y, sigma z I am considering. So it is given like this, epsilon x is given by 1 by e into sigma x minus mu times sigma y plus sigma z. So this how to get this is, so sigma x is the normal stress in that direction only, therefore sigma x by e will be there, and mu is the Poisson's ratio. Since we are taking the strain in the lateral direction, that is for x direction, lateral directions will be y and z. So that's why the stresses in those directions they are multiplied by the Poisson's ratio, and negative because if there is tensile stress in y and z direction, that means if there is increasing length in y and z direction, then definitely there will be a decrease in the x direction. That is why this negative sign has come into picture. Similarly, if you write for the strain in y direction due to all the three stresses, sigma x, sigma y, sigma z, it is written like this: 1 by e into sigma y minus mu times the other two will come here, sigma x plus sigma z. Similarly, epsilon z, that is the resultant stress in z direction due to all the three stresses, it is 1 by e into sigma z minus mu times sigma x plus sigma y. So these three put together, it is called as generalized Hooke's law, which is a combination of Hooke's law and principle of superposition. Now the derivation starts like this. So we have to add all these three now. So if you add NHS, if you add epsilon x plus epsilon y plus epsilon z, that is the sum of the strains, resultant strains in all the three directions, is equal to, if you add the RHS, 1 by e is common, you can take sigma x plus sigma y plus sigma z minus mu times this we have to take, which becomes 2 mu into sigma x plus sigma y plus sigma z. This you can always do this simplification. Now this term epsilon x plus epsilon y plus epsilon z is also called as volumetric strain. So volumetric strain is the sum of resultant strains in all the three directions. So volumetric strain epsilon v is 1 by e into, if you simplify this, you can take this common. Sigma x plus sigma y plus sigma z is common. Here also this is common. If you take the common, you will get 1 minus 2 mu. That's what I have done there. Now this can also be written as sigma x plus sigma y plus sigma z is equal to e into epsilon v divided by 1 minus 2 mu. All these are algebraic simplifications. Now from this what I do is I want sigma x now. Sigma x is this, if you bring to that side, it becomes minus. So you call this as equation 4. Now from the first equation, you take the first equation. So what will be sigma x from the first equation? If you simplify this one, so you will get after cross multiplying, this e into epsilon x will come here, sigma x will be there here. This when you bring to this side, it becomes plus mu into sigma y plus sigma z. This is the other part of equation 1 only. Now from this, what is sigma y plus sigma z? It is nothing but epsilon x minus sigma x minus epsilon x into e divided by mu. Divided by mu will be there. So this is the expression for sigma y plus sigma that we have got. We call this as equation 5. So now 4 is obtained and 5 is obtained. Now what we have to do is we substitute this 5 in equation 4. So for whatever sigma y plus sigma z is there in equation 4, you put this expression. So that means it becomes now, for equation 4 becomes sigma x is equal to e into epsilon v divided by 1 minus 2 mu minus of this one I have to take, because in the place of sigma y plus sigma z I am writing this expression. Now what I have to do is I have to combine the sigma x term to one side. So here sigma x is there. If you bring this minus sigma x by mu to LHS, it becomes plus So then whatever is there this side, so this will be same. This is minus into minus, it becomes plus. So plus epsilon x into E divided by mu. Now here sigma is if you take common, it is 1 plus mu divided by mu. Mu is the LCM, and this term remains same. This term also remains same. Now what you have to do is I have to cancel this mu now. If you want to cancel this mu, multiply throughout by mu. So this mu and this mu will get cancelled. Here one more mu term will appear here. So here 1 plus mu will be there. Here epsilon and E will be there. This mu and this mu will get cancelled. So I am multiplying all the expressions by mu both sides. Now sigma x will be now. So this 1 plus mu will bring to this side. So it has to be divided in both the terms. So it becomes E into epsilon v into mu divided by 1 minus 2 mu into 1 plus mu. Here it is plus epsilon x will be divided by 1 plus mu. You can see here. So just I have combined that. I have put a bracket here. The meaning of this is the entire thing. This entire thing becomes a constant because for a given material, mu is constant, E is constant. Therefore, this entire term becomes constant. So that constant I am going to write as lam is constant divided by lambda. Lambda is the word Greek letter which is used. So lambda into epsilon v plus E divided by 1 plus mu into epsilon x. So like this we got now. So I have written that here. Now in strength of materials we know one more relationship between the elastic constants. So this you should remember. Young's modulus E is equal to 2g into 1 plus mu, where g is the rigidity modulus or shear modulus or modulus of rigidity. So therefore, using this expression, you can write E divided by 1 plus mu as 2g. Now here, that E divided by 1 plus mu term is there here. In this place, I can put it as 2g. Therefore, this becomes sigma x is equal to lambda into epsilon v plus 2g epsilon x. So this is the resultant stress in x direction. So if you know the strain value, you can find out the stress value. So here epsilon x you may be knowing, epsilon v you may be knowing, then elastic constants g, e and mu you may be knowing. Once you know e and mu, you can find out this lambda, and once you substitute those things here, you can get the value of sigma x. So here, this is called as the stress-strain relationship. LHS stress is there, RHS strain is there. Similarly, this I have done by taking in one direction, by considering in one direction. Similarly, you can prove by considering y and z directions. So you can just prove this as, see here, you can write this like this. Sigma x is equal to sigma y. This lambda into epsilon v remains same, plus 2g remains same. Instead of epsilon x, epsilon y will come into picture, and here in case of sigma z, instead of epsilon x, epsilon z will come into picture. So only change is with the last term. So it is epsilon x is equal to epsilon y or epsilon z when you are finding sigma y and sigma z. So that means this is these three relations are called as the stress-strain relations in a three-dimensional stress system by knowing the strains and the elastic constants. So by knowing epsilon x, epsilon y, epsilon z, and also elastic constants means E, mu and g, you can find out lambda and also the stresses. So these three, sigma x, sigma y, sigma z, so these are the normal stresses or direct stresses. Now you can find out the shear stresses also. So shear stresses are obtained like this. So you can directly write shear stresses. So within elastic limit, shear stresses are given by tau xy. So we know that the ratio of shear stress to shear strain is rigidity modulus. Therefore, so tau xy will be rigidity modulus multiplied by shear strain. That is gamma xy. So G into gamma xy is tau xy. So G into gamma yz, it is tau yz, and G into gamma zx or xz, so that is your tau zx. So these three are another three equations which are used to find the shear stresses. So these are used to find the normal stresses. These are used to find the shear stresses. So a problem may be given where they will give all these 6 strain components. 6 strain components are epsilon x, epsilon y, epsilon z, gamma xy, gamma yz, gamma zx, and they may give any 2 elastic constants. Normally they give E and mu. So they ask you to find out the stresses or the stress tensor. So the stresses are obtained by these 3 equations and these 3 equations. Totally you have 6 stress components. They can be evaluated using these 6 equations. So next class I will take up a numerical problem on this.